Right now, if you want to do something incredibly simple, like rename a text file on your desktop
Yeah.
using modern AI, your computer often initiates this sequence of events that borders on the absurd,
It really does. It's completely wild when you break it down.
right? Because you type a prompt, and then your machine sends this signal that travels, hundreds of miles across fiber optic cables.
Yeah, all the way to some massive warehouse-sized data center.
Exactly. And it spins up these water-cooled servers, consuming enough electricity in just a few seconds to power a small refrigerator. And it does all of this just to process a natural language request that your laptop could have theoretically executed in, like, a microsecond back in 1995.
It's the irony of our era. We are currently building the smartest computational systems in human history, but in the process, we are making them incredibly frustratingly bloated.
Bloated is the perfect word for it.
Because we've fundamentally normalized this idea that intelligence requires massive centralized infrastructure.
You mean the cloud?
Right, the cloud. The tech industry has completely conditioned us to accept that to get anything meaningful done, even highly localized personal tasks, we have to tether our machines to someone else's server.
We're basically leasing our intelligence, right?
Exactly. We lease it from a server farm, and we pay for it with our bandwidth, our personal data, and our device's battery life, rather than actually owning it ourselves.
And I think for a lot of people, that tether is starting to feel less like a useful tool and more like an anchor.
Oh, absolutely.
So that brings us to the mission for today's deep dive.
Yeah.
We are going to explore a radical counter-movement happening right now in the AI space.
A movement that is very much needed.
Yeah, because we are unpacking a project that just completely rejects this always-on cloud model. The goal of the architecture we're looking at today is to shrink the AI down, completely sever the cloud connection, and build a blazing fast local assistant that lives strictly on your own hardware.
And the implications of this are just fascinating because they challenge the prevailing business model of the entire tech sector.
Which is all about engagement, right?
Right. We are looking at a system optimized for your personal time and your local resources, rather than a system optimized to maximize engagement metrics for a tech giant.
So, to help us understand how this is even possible, we are looking at a really fascinating stack of sources today.
I was so excited when I saw what we were covering.
I know, it's such cool stuff. The centerpiece is this experimental proof of concept GitHub repository, and it's called Microassistent POC. It was built by a developer named Stefan Meninen.
And it's not just the code we have, which is great.
Right, we don't just have the raw code. We also have translated community discussions, forum posts, and these really detailed developer notes that outline the raw philosophy behind why he even built this thing.
Which is crucial because this isn't some polished corporate product launch.
Not at all. It is highly experimental. It's somewhat fragile, honestly, but it's an incredibly thought-provoking look at where personal computing might be heading.
It serves as the perfect lens to examine the future of AI. But to really grasp what Meninen is attempting here with this microassistant, we have to look closely at the status quo.
Okay, let's set the stage. What is the standard right now?
Today's standard relies on what we call heavy inference.
Heavy inference, got it.
So when you send a prompt to a major cloud provider, you are waking up a model that contains hundreds of billions of parameters. It processes your text, generates a response, and sends it all the way back over the network.
Which inherently takes time.
Exactly. That pipeline is inherently latent. But worse than the latency, that massive model knows absolutely nothing about your personal workflow.
Right, it doesn't know my local file structure or my daily habit.
Not unless you explicitly feed it that exact context every single time you interact with it.
It's essentially a supercomputer that wakes up with total amnesia every single morning.
That is a great way to put it. Total amnesia.
You literally have to explain your entire job to it before it can help you format one single document.
And that amnesia is a direct byproduct of centralization. A cloud model has to serve millions of users simultaneously.
So it can't play favorites.
Right. It cannot afford to fundamentally change its internal structure just to accommodate your specific quirks or how you like your folders organized. It has to remain generalized.
Which is where this project comes in.
Yes. The microassistant concept aims for the exact opposite. An intelligence so local, so small, and so intimately tied to your habits that it eventually stops needing to compute your requests at all.
It just acts.
It simply acts.
Okay, so before we even touch the code or look at the models themselves, we really need to understand the philosophy driving this. Because reading through Manninen's translated developer notes, this isn't just a fun coding exercise on a weekend.
Yo, it is a statement.
It reads like a total, uncompromising rejection of the current AI industry's trajectory.
Absolutely. The foundational principle outlined right there in the repository is a very specific phrase. And that phrase is AI should assist understanding, not replace it.
AI should assist understanding, not replace it. I actually kept circling that phrase in my notes when I was prepping for this.
It's powerful, isn't it?
It really is. It feels like a direct response to this modern trend where, we're constantly encouraged to just hand over our entire cognitive process to a black box.
Just click a button and trust the machine.
Yeah, just click a button and trust that the machine is doing the work correctly in the background without us needing to know how it got there.
And that black box nature of commercial AI is a major point of contention in these forum discussions we looked at.
Right.
Manninen designed this microassistant to be intentionally transparent. The documentation heavily emphasizes that there are no hidden autonomous behaviors.
So no weird stuff happening while you're not looking.
Exactly. You aren't dealing with opaque agent swarms operating in the background, making decisions that you can't trace. And there are zero unnecessary cloud dependencies.
Which means it's all right there on your machine.
Right. If the assistant learns a shortcut or executes a command, that logic is stored locally in plain text. You can inspect it, you can modify it, or you can just delete it if you want to.
And that level of transparency leads directly into what I found to be, honestly, the most counterintuitive part of this entire project.
The core metric.
Yes, the core metric. So the developer established this core metric to measure the success of the assistant. Now, normally, if you build a software tool, success means people are using it more, right?
That's the Silicon Valley mantra.
Right, active daily users.
Yeah.
But here, the stated goal is that API calls, web searches, and model invocations should actually decrease over time.
Which is just a wild paradigm shift. We should probably define what an API call is in this context for the listener because it really highlights why this metric is so subversive.
Yeah, please do. Break that down.
So an API, or application programming interface, is essentially the digital messenger between different software programs. When you use a cloud AI, your computer makes an API call. It packages your prompt, sends it over the internet to the AI company's servers, and waits for a response.
And that costs money.
Yes. Every single time that happens, it costs the provider a tiny fraction of a cent in compute power. And they eventually pass that cost on to you through subscription fees or data harvesting.
So the entire economic engine of the current tech industry actually relies on maximizing those API calls.
Exactly. They want you sending more prompts, consuming more compute, and spending more time inside their ecosystem. The business model is predicated on continuous engagement and continuous dependency.
But this project wants to reduce them.
By optimizing the system to deliberately decrease model invocations, this project is operating on a completely alien paradigm. It is measuring success by how quickly the AI can render itself completely unnecessary for repetitive tasks.
Okay, let me see if I can visualize this because I was thinking about an analogy for this earlier.
Hear it.
Is it kind of like, imagine if I were to hire a massive, high-priced corporate consulting firm every single time I needed my weekly expense spreadsheet formatted.
Okay, I like where this is going.
Right. So I gather all my receipts, I mail them to this firm in another city, and they put a team of 50 people on it. People who have MBAs and have read every financial textbook ever written.
The heavy inference.
Exactly. They deliberate, they format the spreadsheet, and they mail it back. It takes days, it costs an absolute fortune, and the worst part is, next Friday, when I have new receipts, I have to call the exact same consulting firm and start the entire massive process over again.
That captures the inefficiency of the cloud perfectly. The consulting firm, the cloud AI, doesn't retain your highly specific, repetitive daily context.
They start from scratch.
Right. They treat every Friday's spreadsheet as a brand new, highly complex puzzle that requires their full intellectual weight to solve.
But this microassistant, it's more like hiring a dedicated intern who just sits at the desk right next to yours.
Yes, the local model.
Right. So on day one, this intern might not know much about macroeconomics. They actually have to sit there and watch you work. But they notice that every Friday at 4 p.m., you open a specific folder, you copy the data, and you paste it into a specific template.
You're observing the route.
Exactly. So after a week, when Friday rolls around, the intern doesn't ask you what to do. They don't consult a textbook. They just format the spreadsheet instantly because they've internalized your specific routine.
And the calls to the massive consulting firm drop to zero.
Exactly. The API calls drop to zero.
Because the intern builds local context, which is vastly more efficient than generalized intelligence for daily tasks.
It makes so much sense when you frame it that way.
And if you apply that to your own computer usage, the privacy and speed benefits are just massive. You are keeping your data entirely on your local disk.
You aren't waiting for network latency.
Right. The system is optimizing for your time and your machine's resources, not for a corporate dashboard's engagement metrics.
Okay, so if we are firing the massive corporate consulting firm, we have to look at who is actually doing the work locally. What is running under the hood here?
This is where the architecture gets really interesting.
According to the repository, it relies on a dual model architecture. It's a tag team of tiny experts. And when the notes say tiny, they mean a completely different weight class than what we usually hear about on the news.
Absolutely. The architecture specifies the use of sub-1B models.
Meaning fewer than 1 billion parameters.
Yes. And to give some scale for the listener, the frontier models everyone talks about today, the ones running the massive cloud chatbots, those often operate with hundreds of billions, sometimes even over 1 trillion parameters.
Wait, let's pause there for a second. We hear the word parameters thrown around constantly in AI news, but what does a parameter actually do?
That's a great question.
Like, why does a massive parameter count drain my laptop battery? And why is a sub-1 billion model so profoundly different?
Think of a parameter as a single adjustable connection within the AI's neural network. It's roughly analogous to a synapse in a human brain.
Okay, the synapse.
When an AI model is trained, it reads massive amounts of text, and it adjusts these parameters to learn the statistical relationships between words.
So it's learning which words usually follow other words.
Exactly. So when you ask an AI a question, it runs your text through all of these parameters using really complex math, specifically matrix multiplication, to predict what the next word should be.
So if a model has 1 trillion parameters, it has to do the math on 1 trillion different connections just to output a single word.
Broadly speaking, yes. That is what heavy inference is. It requires loading all of those parameters into your computer's memory, which is usually the RAM on your graphics card, and constantly crunching the numbers.
Which takes power.
Immense electrical power. And it generates a ton of heat. Your standard laptop simply doesn't have the memory or the cooling capacity to run a 1 trillion parameter model.
It would just melt.
Pretty much. However, a model with only 270 million parameters, like the one used in this project, is small enough that it can load into the standard memory of almost any modern laptop, or even a smartphone.
Without melting the battery.
Exactly.
Which brings us to the specific models that Stefan Manninen chose for this proof of concept.
Right, the dual setup.
He uses one called Gemma 3.270 meters as the conversational front end, and another called Function Gemma to act as the tool router.
And the division of labor here is absolutely critical.
How so?
Well, Gemma 3.270 meters is strictly handling voice and basic intent detection. You speak to it or you type to it, and its only job is to figure out the general shape of what you want.
Like just figuring out the goal.
Right. It asks itself, does the user want to search the web or do they want to modify a local file? And once it determines that intent, it hands the request over to Function Gemma.
And Function Gemma is the one that generates what the notes call structured JSON actions.
Yeah.
Now, I see JSON mentioned all the time in developer tools, but what does that actually look like to the computer and why is it so necessary here?
So JSON stands for JavaScript Object Notation.
Okay.
It is essentially a universal data format. Its job is to turn messy, unpredictable human language into a strict, highly organized list of commands that a computer program can execute safely.
Like translating poetry into a spreadsheet.
Very close. Human language is full of ambiguity, right?
Yeah.
If you tell an AI, hey, can you go find that file I was working on yesterday and crack it open, a normal chatbot might just reply, sure, I'd love to help you with that. What was the name of the file?
Which is helpful for chatting, but not for doing work.
Exactly. A system that needs to actually execute code can't deal with conversational fluff. It needs strict parameters.
So how does Function Gemma handle that?
It takes your intent and it outputs a JSON block, which uses a very specific syntax of curly braces and key value pairs. So it outputs something rigid, like curly brace, quote, action, end quote, colon, quote, search directory, end quote. Then target, documents, date, yesterday.
Oh, I see. It strips out all the personality and just leaves the raw commands.
Yes. And that structured JSON can then be fed directly into your computer's terminal to actually perform the action.
But, and this is a big boob, but reading through the translated community discussions, Manon is surprisingly blunt about the limitations of this specific setup.
He is incredibly honest.
He openly admits that starting with Gemma 3.270 meter isn't actually ideal. He writes that it requires too much training from the start to be highly effective, and he basically chose it just because there wasn't a better alternative available at that exact tiny size.
The frankness of the developer notes is really refreshing. He is fully acknowledging that a 270 million parameter model is, out of the box, quite ignorant.
Ignorant is a strong word, but fair.
It doesn't have the vast encyclopedic knowledge of a cloud model. It is going to struggle with complex phrasing.
Okay, I have to push back on the underlying logic here, though. If the base model is so small that the creator openly admits it's practically amnesiac, how is this useful to the listener? Why build an entire personal assistant on top of a brain that you already know is vastly underpowered?
It sounds counterproductive, right?
It feels like trying to win a Formula One race with a lawnmower engine.
That's a funny image, but you have to look at what the architecture actually prioritizes. The model's ignorance is an acceptable trade-off because its role is severely restricted.
It's not trying to be a genius.
Exactly. You aren't asking Gemma 3.270 meters to write a thesis on quantum physics or to summarize the history of the Roman Empire. Its only job is that initial routing.
Figuring out if you want to open a folder or search the web.
Yes. The true intelligence of this assistant does not come from the model's pre-training.
It's come from the environment built around the model.
Bingo. Meninen notes in the Swedish text that the absolute crucial point of the project, he calls it the A and O, the alpha and omega, is portability.
Portability.
A model this small can be moved anywhere. You could run it on a Raspberry Pi, embedded in a smart home device. You can run it offline on an airplane.
No internet required.
Zero. The architectural bet here is that extreme portability and local execution are far more valuable long-term than raw, out-of-the-box knowledge.
Because you can fix the knowledge part eventually.
Right. You can always fine-tune a small model to get slightly better at intent detection, but you can never force a trillion-parameter cloud model to run locally on your phone.
Okay, that makes sense.
Yeah.
But if the tiny models are just acting as a front door and they are practically amnesiac by design, they can't possibly remember what you did yesterday.
No, they can't.
Which means the system must have an external memory drive to actually function as an assistant.
And this brings us to the core innovation of the entire repository, the local intuition layer.
Local intuition. I love that name.
Instead of trying to force a neural network to memorize your habits through endless, expensive computation, the system uses a much older, significantly faster technology.
A SQLite database.
Yes.
A database. We are moving from cutting-edge neural networks back to a technology from, the early 2000s.
Even earlier in concept. But relational databases like SQLite are absolute masterpieces of optimization.
They just work.
They don't do matrix multiplication or complex probability calculations. They just store structured data.
And in this case, what kind of data are they storing?
They are storing reinforced routes, cached answers, usage statistics, and feedback weights. And they allow you to search that data almost instantaneously using highly efficient algorithms called B-trees.
So the system is essentially building a structured ledger of every command you issue, logging whether or not it was successful.
Exactly. It's a ledger of your habit.
The developer laid out this brilliantly simple execution flow matrix in the notes to explain how this database interacts with the AI.
I love the matrix breakdown.
Yeah, it operates like a traffic light system that happens before the AI models are even invoked. So let's walk through this matrix for the listener, starting with the first scenario. Red, a cache miss.
Right. So in a red scenario, you ask the assistant to do something, and it checks the SQLite database first.
Always checks the database first.
Always. And it finds that there is no existing policy for what you just asked. You've never asked for this before, or perhaps your previous attempts had negative feedback and were deleted.
So the database comes up empty.
Because the database has no answer, the system is forced to run the full computational pipeline.
This is where it actually has to wake up the AI. And the outline mentions something called MOE happening during this phase.
Yes, the full pipeline utilizes a mixture of experts or MOE approach.
Mixture of experts. How does that work?
Rather than having one monolithic model try to process your request, an MOE system routes your prompt to specialized subnetworks.
So it divides and conquers.
Exactly. Your prompt goes in, and the routing layer decides which expert is best suited to handle it. Maybe one expert is trained specifically on coding tasks while another handles calendar events.
That sounds more efficient than a giant model.
It saves some compute compared to running a massive model, absolutely.
Okay.
But it still requires loading neural network weights into memory, performing matrix multiplication, generating the JSON, and executing the tool.
So the red path is still the slow path. The AI has to do the heavy lifting.
Yes.
Okay, so what happens in the yellow scenario?
Yellow is a routing intuition hit.
Routing intuition hit.
You issue a command, the system checks the SQLite database, and it sees that for this specific request, the write weight is a 2.0 or higher, but the answer weight is still low.
Okay, what does a high route weight actually signify in plain English?
It means the system remembers how to solve your problem, even if it doesn't know the final answer yet.
Can you give me an example?
Sure. For example, if you ask for the current weather in London, the system sees a high route weight indicating, I know exactly which web search tool to use for this.
Oh, I see.
Because it knows the route, it completely bypasses the Gemma 3.270 meter intent analysis. It doesn't need the AI to figure out what you want. It jumps straight to executing the search tool.
You've skipped a massive layer of computation just by remembering the right tool.
Exactly.
And then we reach the holy grail of this architecture. Green. A full intuition hit.
This is where the magic happens. A green hit means both the route weight and the answer weight in the database are 2.0 or higher.
So it has everything it needs.
The system knows exactly what tool you need, and it already has the verified, highly rated answer saved from a previous identical execution.
The performance metrics attached to this green hit in the developer notes are honestly hard to wrap my head around.
The speed is incredible.
When it hits green, it skips the local AI engine entirely, which the developer notes is running through a software called Llama. That's a tool that lets you run these models locally.
Right.
So it skips Llama entirely. The AI stays completely asleep. The system just retrieves the verified answer directly from the SQLite database. And the latency recorded for this action, roughly 0.83 milliseconds.
To put 0.83 milliseconds into perspective for you, a human eye blink takes about 300 milliseconds.
Wow.
The system is retrieving and executing your complex workflow hundreds of times faster than you can even blink.
Okay, I think I have a way to conceptualize this, because this database layer is acting exactly like human muscle memory.
I love this analogy.
Think about when you first decide to learn the guitar. You sit down, someone tells you to play a C chord, and you are squarely in the red zone. A cache miss.
You have no idea what you're doing.
Exactly. Your brain has to actively compute every single step. You're thinking, where does my index finger go? Second string, first fret, middle finger, fourth string, second fret.
It takes immense cognitive effort.
Right. You're staring at your hands, and it takes several seconds just to form the chord.
That is the heavy inference phase. The neural network is actively crunching the problem.
But then, after practicing for a few days, you enter the yellow zone, the routing intuition hit.
You're getting better.
You know what a C chord is. You don't have to look up the diagram in a book anymore, but you still have to consciously tell your hand to form the shape. You know the root, but the execution still requires a tiny bit of active processing.
You've bypassed the research phase, but you still have to execute the physical tool.
And then, after playing that chord 10,000 times over 5 years, you reach the green zone. Full intuition. Someone shouts, play a C chord, and your hand just forms the shape instantly.
You don't even think about it.
You could do it while holding a conversation, while looking away, because your brain has essentially bypassed the active cognitive processing center. It relies entirely on physical muscle memory.
And that is exactly what the SQLite database is doing for the computer. It is building digital muscle memory. For repeated tasks, it stops thinking and just does.
It's so elegant.
The transition from active cognition to automated physical response is a brilliant way to frame this, and it highlights a massive philosophical divide in how AI development is currently being handled.
How so? What's the industry doing instead?
Well, the industry standard for giving an AI memory right now relies on a technique called RAG.
RAG, Retrieval Augmented Generation.
Yes. In a standard AG system, if you ask the AI a question about your private data, it searches a vector database, pulls up a bunch of relevant text documents, pastes them into the AI's context window, and forces the massive neural network to read all those documents and generate a fresh answer.
every single time.
Every single time. It is incredibly resource intensive because the AI still has to do the heavy lifting of reading and interpreting the text, even if you ask the same question yesterday.
Oh, wow. It's like forcing a student to reread the entire textbook every time they take a quiz, just to make sure they still know the answer.
Exactly. It's wildly inefficient. The Microassistent project argues that memory shouldn't just be a pile of documents you force the AI to retrieve and read. Useful behavior should be learned and compiled into instinct.
Into muscle memory.
Right. When the system knows the answer, it optimizes the expensive neural network out of the equation entirely.
Wait, okay, hold on. If the system is bypassing the AI to give you a saved answer in less than a millisecond, that introduces a terrifying vulnerability.
I was wondering when we'd get to this.
What happens if it learns a bad chord?
Right.
Like, what if I ask it to delete a temporary file and the AI hallucinates and it deletes a critical system file instead, and the database gives that action a positive weight?
That would be catastrophic.
Am I now stuck with a hyper-efficient, sub-millisecond automated system that confidently destroys my hard drive every time I trigger that routine?
The rigidity of caching AI responses is a massive risk, and Stefan Maninin clearly knew that, which is why the architecture includes what he calls the cleaner or critic layer.
The cleaner layer.
Think of it as the assistant's autonomic immune system.
An immune system hunting for bad habits.
Precisely. Because the system is constantly logging these weights, it needs a continuous auditing mechanism.
So how does the cleaner work?
The cleaner layer operates in the background, reviewing the SQLite database. It looks at the feedback loops. If an answer or a route consistently leads to errors, or if the user manually flags a response as unhelpful, the cleaner layer degrades the weight of that specific database entry.
It demotes it.
Yes. And if the weight drops too low, the entry is purged entirely. It acts as a strict filter, ensuring that only genuinely useful, highly verified, error-free behaviors are allowed to reach that green, full intuition status.
It's basically the guitar teacher sitting next to you slapping your hand before you permanently memorize the wrong finger placement.
That's a perfect continuation of the analogy.
But reading the developer notes, keeping the database tidy, isn't just about preventing errors today. There's a very specific, ambitious, long-term vision for all this verified data sitting in the SQLite ledger.
Oh, yes. The data generated by this immune system is essentially gold.
Why is it so valuable?
As the database fills up with these repeated, highly verified green hit patterns that perfectly reflect your unique workflow, that data becomes the ultimate personalized training set.
Ah, I see where this is going.
The long-term vision outlined in the repository is to use this database for a distilled local adapter. Specifically, a LoRa.
Let's break down LoRa for the listener, because it's a term that pops up everywhere in local AI communities right now. Low-rank adaptation. What does that actually mean in practice?
So fine-tuning a massive neural network traditionally means updating all of its millions or billions of parameters.
Which takes supercomputers and weeks of time.
Right, it's out of reach for regular people. But LoRa is a clever mathematical trick. Instead of changing the massive base model, you freeze it. You lock it down completely.
Okay, the base model is frozen.
Then you introduce a tiny, lightweight set of new parameter matrices, that's the LoRa adapter, and it essentially sits on top of the base model. And you train only this tiny adapter on your specific SQLite database.
So instead of relying on the SQLite database as a separate memory layer forever, you periodically take all your successful personalized workflows and you use them to train this tiny adapter.
Yes.
You're permanently, physically reshaping the neural pathways of the AI itself.
That is the ultimate goal. Over time, the Gemma 3.270 meter base model, which started out quite ignorant, is combined with the LoRa adapter.
And it levels up.
The AI actually becomes vastly more intelligent, but only in the very specific domains that matter to your daily life.
So it sheds the computational bloat of generalized knowledge.
Exactly. It still won't know the capital of ancient empires, but it will achieve hyper-efficiency in managing your specific coding environment or organizing your unique file structures.
This evolution completely reframes the relationship between a user and their machine.
It really does.
Right now, interacting with a standard cloud AI is purely transactional. You prompt, it answers, and the system resets. The AI itself does not structurally change based on your existence.
No, it stays exactly the same for everyone.
But in this paradigm, the assistant becomes an exact, localized reflection of you.
The software physically adapts its weights to mirror the user. It represents a shift from software as a static service to software as a cultivated entity.
I have to admit, exploring this architecture feels incredibly futuristic.
It's very sci-fi.
It is a hyper-fast, deeply personal AI that learns my exact habits, lives entirely on my hard drive, protects my privacy, and executes tasks in sub-milliseconds.
Yes.
It sounds like the absolute holy grail of personal computing.
It does sound perfect on paper.
But we need to inject a serious reality check into this deep dive.
Yes, we do.
Is this something I can download from GitHub right now, install on my machine, and use to run my life tomorrow?
The short answer is a definitive no.
I figured.
The developer is remarkably transparent about the raw, experimental state of the code. We have to examine the hard limitations outlined in the repository to understand where this technology actually stands today.
Okay, let's unpack the bottlenecks.
Yeah.
What is the biggest hurdle preventing this from being a daily driver right now?
The most glaring limitation is how the SQLite database actually retrieves memory. Currently, it relies on exact hash matching.
Okay, let's explain hash matching for the listener,
Yeah.
because that sounds like a massive vulnerability in a natural language system.
A cryptographic hash function takes an input, like your text prompt, and it scrambles it into a fixed-length string of characters.
Okay, so a string of random letters and numbers.
Right. So if you type, open the data folder, it generates a specific hash. The database looks for that exact hash to trigger a green hit.
That seems simple enough.
The problem is hash functions are perfectly deterministic and highly sensitive. Meaning if you type, open the data folder today, but tomorrow you add an extra space, or you type, open the data directory, the hash changes completely.
And because the hash changed, the system registers a red cache miss.
Exactly.
It completely forgets that it knows the answer, just because you used a slightly different synonym or added a space.
It is extremely brittle. A true natural language assistant requires semantic similarity.
Which means it understands the meaning, not just the exact letters.
Right. The ability to mathematically understand that open the data folder and show me the files in the data directory mean the exact same thing in a multidimensional vector space.
And this project doesn't have that yet.
The current proof of concept completely lacks that semantic understanding at the database layer. It needs the exact string to function efficiently.
That alone makes it really tough for casual use.
It does.
What are the other limitations?
Well, the answer validation process is described in the notes as very weak. The actual execution of tools, the mechanism that allows the JSON to interact with your operating system, is in its absolute infancy.
So it's barely wired up.
Right. And furthermore, those feedback weights we discussed, the mechanism that adjusts the database and builds the muscle memory,
Yeah.
they're currently entirely manual.
Wait, manual?
Yes.
You mean after every single action, I have to physically type it in the terminal, good job, you got that right, or no, you failed, just to adjust the SQLite weights?
In this experimental stage, yes, you have to manually train the immune system.
Wow, that is a lot of work.
It is. And most crucially, that brilliant long-term vision we just discussed, using the database to automatically train a LoRa adapter to reshape the neural network, does not exist in the code yet.
It's not built at all.
It is purely a conceptual goal written in the documentation.
Okay, what I find fascinating is that Stefan Manninen makes absolutely no apologies for any of this.
Done it all.
The support disclaimer in the GitHub repository is just a masterpiece of bluntness. It essentially reads, "This is an experimental proof of concept. No support is promised whatsoever. Issues may be ignored. Pull requests may be ignored."
That unvarnished approach tells you everything you need to know about the intent behind the project. You read the translated Swedish notes, and the underlying ethos becomes crystal clear.
He's not trying to build a startup.
Exactly. Manninen explicitly states that this architecture represents a thought process he has been wrestling with for years. By releasing it under an open-source MIT license, he isn't trying to build the next massive commercial SaaS product. He isn't trying to secure venture capital.
So what does he want?
His goal, in his own translated words, is simply to sow a seed.
To sow a seed. It is the absolute embodiment of the classic open-source hacker ethos.
It really is.
You have this brilliant, wildly ambitious, slightly fragile, half-finished puzzle. And instead of keeping it a secret until it's perfect and ready to be monetized, you just push it to GitHub and say, here is a sub-millisecond local AI architecture. It barely works. It's held together by exact hash matching and manual inputs. But the fundamental concept is sound. Have fun.
It forces us to reflect on how genuine innovation actually occurs in software.
It doesn't always come from the top down.
The most disruptive technological shifts rarely start as polished products from trillion-dollar tech giants. They start as fragile, experimental seeds planted in forums and repositories.
Because the big guys have no reason to build this.
The major cloud companies have zero incentive to build a system that actively reduces API calls and keeps users off their servers. They will ignore this paradigm completely because it directly contradicts their monetization strategy.
So a project like this represents a grassroots push toward digital sovereignty.
Yes, digital sovereignty.
It's a group of developers proving that we don't have to accept the bloated, surveillance-heavy cloud model as the only valid future for computing. They plant the seed. Someone else forks the repository and solves the semantic similarity issue using lightweight vector embeddings.
Someone else writes a script to automate the feedback loop based on terminal error codes.
Right. And suddenly, what started as an ignored proof of concept evolves into a viable, hyper-fast alternative to the centralized tech giants.
It is a technological David and Goliath scenario, played out through system architecture, sub-billion parameter models, and relational databases.
Wow. We have covered an immense amount of ground today. Let's take a moment to recap this journey before we close out.
Good idea.
We started by examining the deep frustrations inherent in the modern status quo. Bloated, cloud-dependent AI models that require massive data centers and constant internet connections just to execute trivial local tasks.
Which led us to explore the counter-movement embodied by the microassistent POC. We analyzed its dual model architecture, utilizing incredibly small models not for their deep knowledge, but strictly for intent routing and generating structured JSON actions.
And to compensate for the amnesia of those tiny models, we uncovered the project's secret weapon, which was the SQLite intuition layer.
The muscle memory.
Right. By acting as digital muscle memory, the system bypasses heavy AI computation entirely for repeated tasks, utilizing a cleaner layer to verify data and achieving staggering sub-millisecond execution speeds, 0.83 milliseconds to be exact.
Ultimately, it is an architectural philosophy that optimizes for extreme portability, stringent data privacy, and personal efficiency.
It fundamentally aims to decrease our reliance on heavy computation, rather than endlessly increase it.
Sowing a seed for a future where technology is highly personalized, self-reinforcing, and entirely locally owned.
Which brings us to the end of our deep dive. But before we sign off, there is a final lingering thought that naturally stems from this entire discussion. And it's something I want you, the listener, to chew on as you go about your day.
This is a really important concept to consider.
Yeah, because we have spent the last hour praising the immense benefits of a highly personalized, self-reinforcing AI that learns your specific workflows. But we must consider the psychological endpoint of this technology.
The natural conclusion of this path.
Right. If this open source vision succeeds and we all eventually possess these hyperlocal microassistants that perfectly mirror our habits, our shortcuts, and our unique problem-solving styles.
Could these systems inadvertently inherit and solidify our personal blind spots?
Oh, that is a profound question. If the AI is only learning from my successful actions, and it relentlessly reinforces the specific paths I take most often to solve a problem,
it creates a closed loop. The system optimizes the AI out of the equation to save compute, which means it stops evaluating alternative, potentially better solutions.
because it already found a route that technically works.
Exactly. By bypassing the vast, generalized knowledge of the cloud in favor of your deeply ingrained personal muscle memory, is it possible that this technology effectively traps us?
Wow.
We could find ourselves locked in a highly efficient sub-millisecond echo chamber, perfectly executing our own limited habits forever, without ever being challenged to find a better way.
A sub-millisecond echo chamber of our own design. Efficiency achieved entirely at the cost of discovery and serendipity. That is a fascinating and slightly terrifying concept to leave on.
It gives you something to think about, doesn't it?
It really does. Well, that is all the time we have for today. Thank you for joining us on this exploration of the microassistant. Keep exploring the repositories, keep building your own tools, and as always, keep questioning the underlying architecture of the technology you use every single day. We will see you next time.